Welcome back to what is now our 10th anniversary of the Isaac Asimov Memorial Panel Debate. I'm the host and moderator, Neil deGrasse Tyson, at this institution. Oh, thank you. Here at the American Museum of Natural History, I serve as the Frederick P. Rose Director of the Hayden Planetarium. Frederick P. Rose he's a great philanthropist. The entire Rose family, in fact, have transformed the landscape of the city in ways that have brought cultural enrichment to us all. The Rose Center is just one example of them. Part of that philanthropy that was going on at that time involved a way to remember Isaac Asimov. Isaac Asimov is no stranger to readers out there, author of more than 600 books. He is a New Yorker, did much of his research in the halls of the American Museum of Natural History, availing himself of our library system, and as a fitting memory to his legacy, his wife, Janet Asimov, and friends endowed this series, the Isaac Asimov Memorial Panel Debate. This is our 10th year, but of course that makes it our 11th panel. If you do the math, that's how it comes out. I want to thank Janet Asimov and the Asimov family and friends of Isaac Asimov for enabling this, what has become one of the most successful programs of this institution. I want to publicly recognize them for this. We have elected in this 10th anniversary of the series to reprise the subject of the original Asimov panel debate. That original debate was on theories of everything, specifically string theory, and what string theory is, what it means, how far has it come, how far will it take us. We thought that over these 10 years, maybe we should check in on string theory, see how they're doing. Oh, by the way, I meant to publicly recognize that we have 300 overflow attendees to this event in an adjacent room. I just want to say hi to them. Can I hear them? Yeah, there we go. Okay. We're not forgetting about them as well. So we're going to revisit this subject. We have two members of the current panel that were on the original panel. That'll sort of ground us with a 10-year baseline. But we have some new people to bring to you, people who have new ideas about what should be going on the frontier of physics. I'd like to lead off introducing Dr. Lee Smolin. Lee, come on out. Lee Smolin. Lee Smolin is one of the founding physicists of the Perimeter Institute of Toronto, an institute that specializes in the fundamental principles of physics and how they might need to change to give us an understanding of the world that we all hope and expect to have. Next, where am I going here? Get my sheets backwards. Hang on. There we go. Next is Jana Levin. Jana, come on out. Jana Levin is professor of physics and astronomy. At Barnard College of Columbia University, she's a specialist in the early universe, especially higher dimensions and what that means. Higher dimensions always confuses us all. So we're going to find out if she can straighten us out and find out what that has to do with theories of everything. Next out, where are we here? There we go, Marcelo Gleiser. Marcelo Gleiser is professor of physics and astronomy, Dartmouth College. We'll find out a little later that I think he actually throws the whole concept of a theory of everything into question entirely. We'll see where that lands. Next up, no stranger to this stage, he's one of the original first panelists of the Asimov debate, Jim Gates, professor of physics, University of Maryland. Jim Gates, come on out. A deep thinker on all matters from the frontier of physics, I always enjoy conversations I have with him by email, by phone, and in person. The fifth of our sixth panelists is Katie Fries. Katie, come on out. Katie Fries. Professor of Physics at the University of Michigan. Katie Fries is an expert on the early universe, and especially dark matter and other exotic phenomena that none of us understands. And last, and certainly not least, is our sixth panelist. Our sixth panelist coming in via Skype. Via Skype. There he goes. Can we hear me on my mic? Yes. Many of you recognize this gentleman. Brian Greene, welcome back to the Isaac Asimov panel debate. It's been 10 years and you look marvelous.
Thank you.
So, Brian, I want to lead off with you. It's been 10 years since we had you on this stage. Before we start, just remind people who you are and what you're interested in and why we might have even asked you to be on this panel at all.
Well, first, I just want to apologize for not being there in person. I had meant to be, but something came up. But I do realize there are some advantages of actually not being there in person. You know, should Neil wildly gesticulate, it's unlikely I'll be the guy that gets hit this time. Should anybody say anything that makes me want to roll my eyes, I can actually do so while still being completely polite just by pulling the curtain right across like that. And finally, this is the first event at the Museum of Natural History I've participated in without wearing any pants. All right.
Brian, later on we'll be asking for data on that. Something string theorists are pretty shy on providing, but go on.
String data, yes. You know, I have worked on string theory since I was a graduate student back in 1984, 85, 86. And I think that perhaps is part of why I'm here. And I have a view of where the approach to unifying the laws of nature has been and where it's going. And I look forward to sharing it with the panel here this evening.
So we'll come back to you on that then, if you think that's headed in all the right directions. Because I know we have panelists that think the directions it's headed might not be the right way. So we'll certainly have a vibrant conversation about that. Katie, can you introduce yourself to us all?
Yeah, I'm a particle astrophysicist, and I'm not used to being the pragmatist in the group, but I work on the dark side. So the dark matter, the dark energy, dark stars. And in my view, the theory of everything needs to provide answers not only to questions about the four forces of nature, but also about the content of the universe. It's dark matter, it's dark energy. In fact, this is one of the central questions of our time as scientists, and we're fortunate in that it looks like some of these answers are beginning to come in. So, in my view, the theory of everything needs to tie together with the experimental results we're starting to get out of the dark matter and dark energy regime. So to make sure everybody knows what this problem is, when you think about the chairs that you're sitting on, the air that you breathe, the walls in this room, the planets, the stars, all of that, all the atoms in the universe, all the quarks, all the leptons, all that adds up to only 4% of the universe. And we don't know what the other 96% is. So that's what I work on.
Wait, do you work on the 4% or the 96%?
The 96%.
The 96%. Okay, so you're
96%.
steeped in abject ignorance. That's what you're telling us. Okay. We'll get back to you on that. Jim.
Hello, my name is Jim Gates, and in some ways I owe my presence here to Isaac Asimov. As a kid, I was an avid reader of many of his science fiction works, and I even know who Paul French is, and you have to ask the family who that person refers to. As a young theoretical physicist, I had a dream. You know, like, I'm a black man. Never mind. I had this dream that if I got a chance to do this kind of work, I could find a magical piece of mathematics that was simultaneously an accurate description about things in our world. And I think I'm really close, and I'm going to share with this audience tonight, for the first time in front of any audience, where this place leads us.
How old were you when you first started thinking mathematically about the universe?
I started thinking about wanting to be a scientist when I was age 8. About the time, a little bit before I started reading science fiction.
Okay, so you've been at it for a while. So we expect really great deep thoughts out of you for this.
Wait a minute, you said I've been at it for a while. Why do you say
Oh,
that?
excuse me. Just a few years, yes. Marcelo Gleiser, yes.
Right, so I am a theoretical physicist, and I grew up in Rio at the beach, but also thinking about the stars. And I started my PhD, I did my PhD in string theory and extra dimensions and all those things, and postdocs and all that, and published papers on it. But after a few years, actually a few years back, I started to think a little differently about our efforts to unify all theories into this single theory of nature. And let me just give you one quick story. There was this week in the New Yorker, there was a short story by David Foster Wallace called Backbone. And it's very briefly, it's a story of this little boy who at 6 years old, he gets this idea in his head that he has to, quote, press his lips through every single inch of his body. And he devotes his whole youth to this. He starts doing all these contortions, and he starts spreading his lips so that he can touch every possible place in his body. But then, of course, he looks at the back of his head and the crown of his head with this tremendous mystery, you know, places which are almost sacred. And the story ends basically with a statement which is that, and he has never for a second doubted that he could do it. And yet, of course, you know, he never can do it. And the point is that in the process of trying to do it, he became a wonderful contortionist, and the pursuit of the goal led him to something, right? And I'll just leave it at that as an allegory for our search.
Wait. So you get your physics insight from fiction stories in the New Yorker magazine. That's what you're telling us.
Of course, absolutely.
Okay.
Are you calling us contortionists?
Yeah, are physicists contortionists? Is that your conclusion?
Mine and David Foster Wallace's intention.
We'll find out. Jana, what's been keeping you busy?
Yeah, actually, the past few years I've been interested in more practical aspects of science. So I work on black holes, but black holes are real astrophysical objects, and I remember when I kind of made this shift to thinking about black holes as the death state of stars, and wanting to work on the possibility that black holes ring space like a drum and actually kind of make a sound, play a song on space itself, and that these are things that we can detect one day, that this was a real shift to real things. I remember thinking, you know, on my deathbed, I just want to work on one thing that's real. I do also work on extra dimensions. I'm very interested in the ideas from string theory or other theories of everything. The idea of extra dimensions actually predates string theory. And the implications that these ideas have for understanding the early universe. And ultimately also the cores of black holes, because these are things that we will not understand without more ideas than the ones that we have in our toolkit right now. So theories of everything are still crucial to pursuing even practical things like, you know, black holes. And so I guess that's what brings me here today. But I also have sort of vague ideas about the general paradigm for why we pursue a theory of everything, or if it's even something that we'll ever get our hands on.
Thank you. Lee, you ran off to an institute where all you have to do is think about the fundamental laws of physics. That's deep.
I'm very, very grateful for that. And you know, thank you. I'm very honored to be here, and also it's very nice to be here. Maybe something that the audience will pick up is that we all know each other, and there's a lot of knowledge and history here, and nonetheless I learned something about each of the panelists even so far, even as well as we know each other. It's especially great to be here and to be back here because I was a kid just a few blocks from here on 93rd and Central Park West.
Native New Yorker.
Mm-hmm. Native New Yorker. And it's, even though Toronto is the future, is the city of the future, and it's great to be there.
He's a founding member of that institute, so he's got to say all the right things. Yeah.
It's great to be here. I didn't start out like some of the other panelists, or unlike some of them. I didn't start out wanting to be a scientist. I started out first wanting to be a rock and roll musician, and then an architect. And then that led me to a book of essays by and about Einstein that I picked up when I was a high school dropout at about 17. I think Janet was also a high school dropout,
That's
so we
true.
have that.
Yes, we have that in common.
Now they tell me this before I have them on the show.
And in that book, there was an essay by Einstein, and in it, and he was writing in his later years in about 1950, and he said that there were two problems that he had tried the last years of his life to solve unsuccessfully. And one of them is to make sense of quantum mechanics, which he never believed. And the other is to unify physics, and particularly to unify gravity with the other forces and with quantum mechanics. And for some reason, although I had had no interest in being a scientist before that, I read that essay and I felt like I had a mission, and something clicked and said, you know, I'm not very good at math, but maybe I can do that. And that's what led me to be here. And I have to say...
So we need you to help other high school dropouts. This is a remarkable...
Sure, no, for sure. And of those problems, the problem in the foundations of quantum mechanics, when I learned more and was thinking about what to do in graduate school, I decided that was too hard. Although the last few months, I've actually, for the first time in my life, had a real new idea about the foundations of quantum mechanics. But the other problem, the problem of unification, particularly of the unification of quantum theory and gravity, is the one that I decided to work on. And I've worked on that most of my life. And I've worked on different approaches to it. I have worked on string theory, which is the subject of our discussion. But most of my work has been on other approaches, what we call background-independent approaches. And I hope that that term in that discussion comes up, particularly loop quantum gravity, but also other approaches. And it's been deeply humbling to have the opportunity to work for one's life on these compelling problems about space and time and what is the nature of nature, as Feynman put it. And I look forward to discussing where we are in that search tonight.
Well, excellent. Thank you, Lee. So what we're about to do right now, which is the hallmark of this series, is we're going to break into conversation as though you are eavesdropping on a debate we're having at a bar or somewhere or a coffee lounge, and you're eavesdropping on our discourse. Okay? That's what's about to happen. Brian, it's been 10 years since you were here. I'd like a report from you on what kind of progress has happened in string theory. I don't read the journals on string theory. And so has there been progress or not? Because some of us were skeptical back then.
Yeah, I mean, there's definitely been progress. One question I do have, is it worth setting any ground basic material? Is everybody in the audience familiar with string theory?
Yeah, can you give us, sure, give us in one sentence what string theory is.
It'll be a long sentence.
Use commas and semicolons. No, just, yeah, so let's lay that groundwork. Go ahead.
In less than a minute, you know, the major developments in physics in the 20th century, as I think many people in the audience know, the general theory of relativity is one of the major developments. That's a theory of gravity, which is relevant when things are really big, stars, galaxies, and so forth. The other major development, quantum mechanics, is for the small things, molecules, atoms, and subatomic particles. The thing is, each of these two theories works in their own realm. But when you try to meld them together, it is very, very difficult to get the mathematics to work. The two theories are, in some sense, ferocious antagonists when you try to meld them together. And there has been a push for a long time to try to meld them because there are realms in the universe where you need both the theory of gravity and the theory of quantum mechanics. The center of a black hole is a good example. A star collapses to a very small size. It's massive, you need a theory of gravity. It gets very small, you need quantum mechanics.
Because its size is as small as quantum phenomena would require.
That's right. Its size is small in terms of length. Its size is big in terms of mass. So you need both general relativity and quantum mechanics together, and the Big Bang provides another good example. So this is one of the main motivations for trying to build a unified theory. And perhaps as a footnote, I should say, we may have slightly different definitions of unified theory as the evening progresses that may become clear. The most basic version would be uniting quantum mechanics and general relativity, and that is one of the hallmark features of string theory, that at least on paper, that's what it does.
So
Now-
in the past 10 years, has there been much progress on that? Because
There's-
you look very hopeful back then.
Yeah, no, there's been an enormous amount of progress in string theory. There have been issues developed and resolved that I never, frankly, thought we would resolve 10 years ago. We've been able to, for instance, crack certain fairly impenetrable mathematical aspects of the theory, allowing us to go far beyond the approximate techniques that were the only thing that we really had at our disposal some 10 years ago. And this is a fantastic step forward. Where we've not made great progress is in making definitive, testable predictions that can be tested. And this has been one of the major issues about string theory for a very, very long time. So let me just be very clear so that the baseline is really set. If you were to ask me, do I believe in string theory? My answer today is the same as my answer 10 years ago, which is no, I do not believe in string theory. I only believe in things that are experimentally proven or observationally proven. Do I think string theory is one of our best approaches to putting gravity and quantum mechanics together? I do, and the progress over the last 10 years has only solidified my confidence that this is a worthwhile direction to pursue.
So you're using the word confidence in place of your belief.
I think confidence is a much better word than belief. Belief, I think, is a murky word. I mean,
Okay.
in science, what you do is you have a theory, and you never, ever know whether that theory is right, because you could do 1,000 experiments, and they all confirm the predictions of the theory, but the 1,001st experiment may not confirm the theory. So experiment after experiment can bolster your confidence that a given approach is correct.
Except we're really
But-
just looking for one experiment, right? Not 1,000. We want the
would
first
just
experiment.
that. Yes.
Right.
Now,
Jim, do we have experiments that can...
Well, actually, I was. Hi, Brian. Good to hear from you again. I wanted to actually break in at this point because, in fact, one of the most exciting parts of string theory may be related to superconducting materials. There's a Nobel Prize that was given recently for a material called graphene. It's a remarkable material made of carbon, and it may replace silicon as we make computers in the future. But in order to understand how this stuff works, you actually have to have a mathematical theory.
Wait, so this graphene was this thin layer.
Thin layers of carbon atoms that have truly remarkable
They're like
properties.
one atom layer thick.
Absolutely, absolutely.
Graphene.
Yeah. And it turns out that if you want to understand graphene, there is some evidence that string theory is the only piece of mathematics that can solve certain problems. In fact, the Nobel...
Wait. Just to wait. So there's string theory as a physical concept. Then there's the mathematical tools invoked for it. Are you saying string theory, the concept, can apply to graphene, or the math that they're working on is useful to you as well?
It seems as though string theory, the concept, can be useful for understanding graphene. The recent Nobel Prize winner himself was shocked by this.
So obviously he wasn't the one who came up with it. So one of you string theorists knocked on his lab door.
He also said he doesn't like theorists in general, not just string theorists.
You contaminate their lab. So Katie, you work in the real world here. So compared to anyone else on this panel, you think about real objects. How do you see this marriage of gravitation and quantum mechanics as mattering, as a goal, as mattering to your frontier on the early universe?
One of the big questions is trying to understand the large-scale structure of the universe. Where do galaxies come from? Where do clusters come from? And it turns out you need quantum mechanics on the tiniest scales, but at the earliest times, to get that process started. So we think there's an inflationary epoch of the universe where it was accelerating its expansion at very early times. And in those theories of inflation, where you take a small patch of the universe, blow it up to be very large, and hence explain...
When you say blow up, you mean expand it.
Expanding,
Yeah, because when stuff blows up in the universe, that usually means something else.
No bang here, no.
Okay,
Yeah.
expand.
So it expands faster than the speed of light, and then our observable universe fits inside this giant patch. But one of the big bonuses you get out of this theory is that there are quantum fluctuations on absolutely the tiniest scales, which also get blown up to larger scales, not in the explosionary sense. And can serve as seeds for explaining galaxies and large-scale structures. Without quantum mechanics, on the smallest scales, we wouldn't have those.
So what you're saying is that there's a macroscopic fingerprint that is traceable back to the microscopic phenomena.
Absolutely, and if we're lucky, we can actually use this to test some of the ideas of string theory. In fact, Brian has worked on this by looking at imprints in the cosmic microwave background.
So we think the cosmic microwave background, this is this residual light signature of the Big Bang, might, because it has signatures of other things going on in the early universe, you think string theory might be there as a signature as well?
Well, we've seen the imprints of these quantum fluctuations on the cosmic microwave background, as well as on the large-scale structure. So those are actually observed. You can see ripples in this radiation. But the details of that, you have to ask, well, where were these quantum fluctuations imprinted? And if it was early enough, you might see signatures of string theory. So there's that hope.
Yeah, sure. So, but Lee, this all assumes standard quantum physics, right?
Sure.
Is that okay? Or are you taking us someplace new?
Well, I was going to contribute to this discussion. I'm happy to go to that discussion later, but because just to get specific, because there's an interesting proposal which has come up in some quantum theories of gravity, particularly in what's called loop quantum gravity, that quantum gravity has a property called chirality. Chirality is asymmetry between left and right, or asymmetry under looking in a mirror. And this is a property that particle physics has, particularly neutrinos in the weak interactions. And
Wait, just to clarify, you're saying there's an experiment you can do on this side of the mirror, and it has one outcome. And if you do the experiment in the mirror image of that, you get a different result.
you get a different result, yes. And that's a result in particle physics. It's now very well understood. The standard model of particle physics, particularly the weak interactions, has that property. Gravity, as a classical theory, does not have that property. Gravity, as a classical theory, is symmetric, left to right. Gravitational waves, which are polarized left-handedly, have the same properties as gravitational waves polarized right-handedly. Okay, but in some forms of quantum gravity, that's not true quantum mechanically, and recently some of us have understood that leads to a prediction for the cosmic microwave background fluctuations that Katie was talking about. And I'll say it in language halfway between technical and non-technical language. There are modes of the cosmic microwave background radiation called the tensor modes that, if they're there and if the story of inflation is right, are quantum gravity effects. They're quantum fluctuations in the gravitational field amplified or expanded or blown up, as Katie was describing. And there is a possibility in the Planck satellite of seeing asymmetries left to right, or parity asymmetries coming from parity asymmetries in quantum gravity in the production of the tensor modes. And this is an experimental possibility that, if it's there, I think would knock all our socks off.
Now, of course, the problem is these tensor modes, although they're predicted by every inflationary theory, in many models are quite small, and you won't see anything. And that can you go back and rule out?
Yeah. So wait.
Now, let me just say one technical point to Katie. If these are there, they're not down by there's a ratio of how small the tensor modes are compared to the scalar modes. You're usually looking for things which are in the square of that quantity. But if there's
So what you're saying, wait. So to clarify, it's not the existence of this in the microwave background that would support the theory. It's the measurement of how much it is relative to.
Yes, but there's also an opportunity, because a parity breaking effect in the tensor modes would show up much before the tensor modes themselves, because they would show up in correlations with the temperature modes.
Oh.
All right. So you're saying
so it's a great opportunity for fundamental physics.
So Lee, the current data on the microwave background is insufficient to distinguish this. You need data from this next satellite,
from the
Planck satellite,
which
is a European satellite, if I remember correctly.
It's taking data now.
Taking data now.
Yeah, so we're looking forward to this.
When will we have these data?
Katie would know better than me.
Yeah. No, I don't know either. Just 2012, I think.
It's always just a year away.
It's always just a year away.
How'd you guess?
That's better than 10 years away.
Better than 10 years
No,
away.
I think it's true.
No, I know. And the thing that's really weird that I didn't think that we'd get to such a technical discussion, but in fact, this asymmetry he's talking about is also present in string theory, so I'm not sure it would help disentangle everything at all. It might make the picture much, much murkier.
Let me ask Brian. Brian, what's your best experiment you can suggest for this? Is something in the Planck data that you'll...
You talking very specifically about astronomical observations?
Yeah? You got some other kind of observation? Observations of the universe.
You're asking about how might you test any of these theories. Yes, I think astronomical observation, that's one promising place, which, again, at first sight is a little weird because if we're talking about theories that deal with the quantum nature of particles, maybe the quantum nature of space and time, why would we look up there? But, Katie's explanation is good. An allied one is, if I had a balloon that had no air in it and I scribbled a little tiny message on the balloon, it would be too small for you to see it, but blow air into the balloon stretches, you can read the message on the surface of the balloon. Similarly in the universe, if the young universe got imprinted with some of the effects of quantum gravity or string theory, very, very small, but over 14 billion years of the expansion of space, that little imprint gets smeared out on the sky, and you just need to know what to look for. So Lee is suggesting to look for this chiral property of gravitational waves from the early universe. Calculations that I've done in string theory suggested to look for other kinds of features in the microwave background radiation, which again are very small, too small I think for us to have seen yet, but it could be that Planck may see evidence of them. So I'm excited about that direction, but I do consider it a long shot.
Jana, what's all this about higher dimensions? Could you take us there? Because I live in 3D and I...
Right now?
Right now. Take us there intellectually, whether or not you visit there physically.
Yeah. Well, it is an interesting concept, the idea that there would be an extra direction that we can't point to. It's kind of a frustrating idea. But you have to imagine that that extra direction is everywhere in a certain sense. So if you imagine a plane, and imagine you were this classic flatland creature, in I think it was 1882, Edwin Abbott wrote this beautiful parable of Victorian society called Flatland. And all the characters in Flatland indeed lived in this plane, completely unaware of the third dimension.
Some were triangles, some were
Some are
squares.
triangles, and your social status is related to how many sides you have as a polygon. The high priests are circles, they have so many sides, and the lowly workers are triangles, and our hero is a square, and women are lines, they have no sides. But it was very satirical.
Yeah,
it was
left
very.
out. They can only therefore be seen if they shimmy, which was a little
Right,
bit.
they had to shimmy. And coup.
But women are lines.
Yeah.
Lines, that's what
Women
you
are lines.
They're
they
only
have to shimmy a
one-dimensional.
bit.
This was
But-
1882.
But but you see, he was being he was definitely making a social commentary. He was a progressive person who was making a social commentary about Victorian society. But women could kill their husbands if they didn't see them come in edge on, and they could pierce them. So there was a high mortality rate amongst husbands, which I thought was fair, Anyway, so in
Flatland by Edwin Abbott. It's available. It's a Dover reprint. Go on.
Right. But the Flatland does a beautiful job of challenging you to imagine what it would be like to perceive a third dimension if you were two-dimensional. How impossible it would be for a two-dimensional creature to point up. And yet up is everywhere. Everywhere on that plane, there's an up and a down. But those Flatlanders, they can only see north, south, east, west. They're completely unaware of that third dimension. And that would be our situation if there were extra dimensions. We feel like we're three-dimensional. It looks like we're three-dimensional. But there would be these other dimensions that we simply can't point to, are very difficult to describe in any language other than mathematics. Luckily, we can do it with mathematics, which is a beautiful gift. But those extra dimensions would be everywhere, at every point in space-time.
So how do you invoke them? How do you invoke it?
Well, so one of the big questions, I think that...
I don't deny them mathematically. I can go
right,
with it mathematically.
But even Einstein started, very soon after Einstein first started to propose that space-time was something mutable and evolving, that it could grow and stretch, expand, collapse. People started asking, well, why should there only be three dimensions of space-time? And so this is a very old idea that really predates string theory, although string theory requires a certain number of dimensions for internal consistency, so it's been foisted back on us again. But the great question is, why don't we see these extra dimensions, which I think is what you're getting at. Why don't we see them? It might be that they're very, very small, literally too small for us to stick our hands in, or it would take too much energy to bust our atoms into that transverse direction, or it might be that we are somehow confined to a three-dimensional kind of a membrane, much like the Flatlanders were confined to their plane. So I think there are a lot of ideas out there.
Okay,
Or
that's
it might
fine.
be that they're not there.
But they might
What was
not-
that?
They
It
might
might be
not-
that they're not there.
It might be that
Exactly.
they're not
It might be they're
there.
not
It might be
there.
that there are no extra dimensions. Like Brian said, it's not a matter of believing in things. You know, nature doesn't care what I believe. But these are very interesting ideas that have some very compelling consequences, and we might not have to wait for the hardest experiments to see them.
What we have to do is go to the highest energies at accelerators to the point where you
Currently not in America.
Right, right.
can send
In Europe.
something off into the extra dimension.
Right, so the Large Hadron Collider, which got a lot of press because there was an injunction against it in case a black hole was created and it destroyed the world, which I think is a reasonable risk for the advancement of science. No, I'm just kidding. People were aware of the possibility of making microscopic black holes and things like that. But the LHC, the Large Hadron Collider in Europe, may see signatures of extra dimensions, as Katie's saying. They may get particles going at high enough energy that you can spew something into this extra direction and get a missing signal. Something would suddenly sort of disappear out of your
So
experiment.
you would interpret that as losing something into another dimension.
Well,
And if that's the case,
yes, it's
let
possible.
me ask you, if that's the case, could there be some other activity going on in other dimensions where they punch a particle through and it shows up in our space? And if that's the case, is that what particles are that pop in out of the vacuum? That we say mysteriously, these are like virtual particles popping out of nowhere? Could we be reacting to experiments gone bad in another dimension?
I can say this. I don't think virtual particles don't require extra dimensions, but you could say something like this, like Marcelo and I feel like we're completely independent entities, but actually there's a string connecting us that's going into the extra dimension, and when it intercepts the three dimensions, it looks like a particle here and a particle there that look disconnected, but indeed could be connected.
Yeah.
So the thing that was exciting is that Einstein wrote his paper in 1915, and in 1919, only 4 years after
It's the
that,
general relativity paper.
Yes, his GR theory. And in 1919, just 4 years after that, this mathematician called Theodor Kaluza said, you know what? If instead of having 3 space dimensions, we had 4 space dimensions, I can arrange things in such a way that my theory becomes a theory of gravity, which was Einstein's original idea, and electromagnetism when it's seen in 4 dimensions. So you go from 5 to 4, and in our perspective of 4 dimensions, you actually have these 2 forces, but if you could see them, you know, with 5-dimensional goggles, you actually would see them as one.
Yeah,
So you'd be
it's
unifying
incredible.
the forces in higher dimensions, and in our lowly 3-space, one-time dimension, it manifests itself as these separate entities.
Right.
Can I say it in a slightly different
Sure.
way? If I look at that lamp, I think I'm seeing light, which is a phenomenon that's completely different from gravity, which is keeping the Earth in orbit around the sun and keeping me pinned to this chair. But as Marcella's saying, the big insight at that time, very shortly after Einstein's paper, was that maybe it's all gravity, it's just gravity in higher dimensions, and that from our 3-dimensional perspective, that looks very different from gravity, but it's actually gravity in a higher dimensional universe.
But Marcel, if you're going to tell this story, you should tell a few years after that when Einstein gave up the idea.
Well,
And
it's
Einstein-
flawed.
So that sounded
Einstein-
promising, Marcella, but
No,
It's very
Einstein
exciting.
died trying to make this work.
No, but
not
Einstein
in
gave
5
up the
dimensions.
idea, okay, for a reason I think is very relevant, and let's see what Brian thinks, but very relevant for the last years of development in string theory. Einstein gave up the idea because in general relativity, the geometry of space and time are dynamical, and if the geometry of these extra dimensions is dynamical, then they wouldn't stay small if they needed to be small to reproduce the difference between electromagnetism and gravity. They would grow or they would expand.
So they're not stable.
So they're not stable. And making them stable has been an enormous challenge that I think we may disagree about how elegantly this problem was solved, but a lot of progress in string theory and a lot of the twists and turns of the development have rested on attempting to solve this problem.
Brian and I wrote a
That's
paper
right.
together about it.
Wait, I'll get to Brian in a minute. Jim, how many dimensions do you live in?
I live in precisely 3 spatial and 1 dimensional. 1 temporal. I'm a higher dimensional refusenik.
You're a refusenik of
Yes,
higher dimensions.
absolutely. Because in fact, it turns out that string theory is actually so bizarre that there are versions of it that don't have higher dimensions. This is not very often discussed, even among the physicists, but in the late 80s, this was actually shown, not as conclusively as some of our other versions, because they're not as simple. So this whole discussion of higher dimensions, I think, takes a direction that one should be perhaps thinking with a grain of salt.
Because what I worry about is you invoke a higher dimension when you can't solve your problem. So it's this kind of Band-Aid. Oh, here's stuff you can't see, you'll never interact with. Let me invoke it so that I don't look like an idiot trying to understand my own universe. Brian, how many dimensions you live in?
Well, I think it's a good question. And let me I'll give you a number at the end of what I say, but just to respond to what you just said.
Okay, keep us in suspense, fine.
Just to respond to what you just said, it is not at all that we can't solve a problem, so we pull extra dimensions out of a hat. That
Sure
idea
looks that way.
is completely wrong.
I'm glad, I'm just saying it looks that way.
That's fine.
In a
but
higher dimension, it looks that
and
way.
I'm going to try to disabuse you of that misconception. What we do is we follow a mathematical structure that we believe has the capacity to put gravity and quantum mechanics together. This approach that we've discussed, string theory, or Lee's approach is another approach. But when we follow the particular mathematical equations of string theory, they take us to the idea of extra dimensions. We don't go out looking for it. It's an idea that comes to us. Now Jim's point, if you want to discuss it, to me is a bit of an interesting footnote. In these other versions that appear not to have extra dimensions, they have other degrees of freedom, features that sometimes can be interpreted as extra dimensions. It's a point well taken. But the bottom line is we don't stick it in from the outside. It comes to us from the mathematics. Now, the actual number, the current version of string theory that we take most seriously has 10 space dimensions in one time for 11 total space-time dimensions. It's an approach that you may have heard of called M theory. It unites all of the previously thought to be distinct string theories into one unified framework, and that's the approach that most physicists in this field are studying.
I have to ask, was there ever an idea that had more than one time dimension?
Yes, absolutely. So, Itzhak Bars was one of the people at USC who's pioneered this possibility. He has studied theories with two time dimensions. They're much harder to make work. I mean, if you have trouble thinking about extra dimensions of space, try thinking about extra dimensions of time. I mean, would one of those notions of time sort of align with psychological time and the other would be a different kind of time? I mean, if you show up late, would that mean, yeah, I'm late according to that time? But that's really just facetious. There are really mathematical challenges about having two time dimensions that are very, very difficult, but people have studied it and some progress has been made.
Katie, what are you saying?
I was just going to say that the extra dimensions offer us a tremendous playland in cosmology. We have a lot of fun. So this idea that we're living on a three-dimensional membrane in higher dimensions, motivated from M theory, one version of this is that there would be two such brains at the end of the
Brain, not human brain, but membrane.
membranes at the end of the world. So that's it. That's the end of the space-time. And in between, only gravity can exist.
Or propagate through it.
Only gravity can propagate through it. So one of the consequences of this is that it makes us look again at the equations in four-dimensional theories. And for example, one possibility emerges that Einstein's equations in four dimensions have to be modified depending on what is going on in the extra dimensions. Now, this may actually be a good thing from the point of view of trying to explain the dark energy of the universe. This is
the mysterious pressure that's accelerating the expanding universe, that nobody knows what it is.
Yeah, we see these supernova explosions, which are the end products of stars. When stars die, they explode. And you know exactly how bright the supernova are. It's sort of like holding up a 60-watt bulb in the back of the room. So you know how bright it really is.
A standard candle.
A standard candle. But then it's not looking as bright as it should. And so the interpretation is, well, that's because the person holding that light bulb is running away from me. So the accelerating universe would be an explanation. And we call this, out of ignorance, the dark energy, this negative pressure that drives this acceleration.
But do you need higher dimensions for that? Or maybe you don't know if you need higher dimensions.
We don't know, but it is certainly in It is certainly one of the big puzzles that keeps us all working to try to understand how you can, what can you do, either using modifications of the equations coming from extra dimensions, or back to Einstein, his cosmological constant that he wanted to abandon, but perhaps here we have this reappearing as an explanation for this anti-gravitational acceleration.
So I want to shift gears a little bit right now because basically we've been grounded in the kinds of thoughts in physics that's been driving research over these years. But I want to sort of, Marcelo, you came to the Hayden Planetarium a few months ago and gave a talk that dumbstruck many people in the room because you came at it from a whole other place. What is that place that you come from?
Right. So let me just clarify one thing, which I think is extremely important that maybe all of you know. But when people talk about theories of everything, in physics at least, we don't really mean everything. You know, it doesn't mean that we'll have a theory that will predict where I'm going to have dinner tomorrow, or if I'm going to have a haircut, or something like that.
Okay, so it's a theory of some stuff.
It's a theory of some stuff, and it's really relegated to how the fundamental particles of matter interact with each other. Okay, so the notion that we know now is that there are four fundamental forces in nature. Okay, the gravity and electromagnetism that we know, and two others that live inside the nucleus, the strong and the weak force. So the notion of a theory of everything, or a unification, is that we want to bring these four forces into a single force. So that if you look at very, very high energies, i.e. very close to the Big Bang, close to the origin of the universe, you wouldn't see four forces, you would see only one. So that is the pursuit, that if you look at nature at higher and higher energies, hence the interest in the LHC, for example, you'd actually start seeing things to look more and more alike, particles interacting in more and more similar ways, all the way up to this unified theory.
So it only looks like four forces because we live in a relatively cold part of the universe.
Exactly. Right?
All right, so Einstein died trying.
He did. He spent, 20 years trying to unify only the electromagnetic and the gravitational interactions into a theory in 4 dimensions, as Lee was mentioning there. And people nowadays would say, well, he couldn't have succeeded because he left 2 very important forces out. We now know that there are only 4 forces of nature. And I start thinking, well, how do you know that? Well, that's what we measure. But how do we know about nature? Well, exclusively through our measurements. What we need in order to make sense of reality is our tools. And a lot of discovery in physics, not completely, but a lot of it is very much dependent on the accuracy of our instruments. If you look at the history of quantum mechanics, for example, it wouldn't have happened if we didn't have the right machines, the right laboratory experiments to force people, brute force people into thinking in a completely different way than they were thinking before. It was a real time of drama in physics where the old folks would not want to give up the notion that everything is deterministic and ordered, but experiments forced them into this. Einstein, when he came up with relativity, he had very specific tests of his theory. And eventually, when the tools were allowed, were there, people went out, measured, for example, the eclipse, during a solar eclipse, you could measure stars and look at their position with respect to when the sun is not in the path, and you find a little distortion which has to do with the curvature of space that he predicted would be there. So a lot of what we know of the universe depends on how we measure things. And to me, the problem with the notion of a theory of everything is that it implies that we will eventually know everything there is to know in the world of particle physics only, that we're going to have tools that will be able to give us all the answers that we're looking for. And I do not see how that's possible. For example, let's say we succeed with a 10-dimensional, 11 space-time dimensional superstring theory, which is a wonderful thing, and I'm completely in agreement with Brian that it is about making it falsifiable, making it testable, and that's perfectly okay. What bothers me is not getting there. What bothers me is saying that that is the answer, that is the theory of everything, because very possibly a few years from now, a new machine, as has happened on and on and on in the history of physics, will reveal something completely unexpected that will need new ideas for us to keep going. So for me, physics is a work in progress, is a narrative, is an ongoing effort for us to understand nature.
The endless frontier.
The endless frontier.
And if it's endless, you then can't have a theory of everything.
Right, you make your knowledge grow like an island, you know, but then the shores of your ignorance increase.
Yeah, but
Is
what?
this a question of language?
Can I?
Yeah, but wait,
Yeah.
but Marcelo,
Wait.
but that sounds like almost wishful thinking. There are things we do understand, and the shoreline of the island does not keep growing. We find another island, but the shoreline of the island we've been studying works. We predict within it, and it doesn't. And we're done. There's certain things about physics that we're done.
We do progress.
but
I mean, you
we-
can't
The
claim we
DARPA
don't progress.
It depends how deep your questions are. Okay, so you say, look, Newtonian gravity explains how, you know, how the Earth is going around the sun. Everything is a beautiful thing. And then you start to think, okay, but how is matter attracting matter? Well, you say it's the curvature of space, which is what Einstein said. But then you say, but why matter
No,
attracts
I'm with you there.
space?
I'm with you there. But hear me out. Hear me out.
Okay.
Using that analog, you have Newton. That works for like horses and stuff. And then Einstein, you need a new understanding that modifies Newton to get high speeds and high gravity. All right? So that's not something separate. That's not a separate island. It's a bigger island
Yes.
with more understanding of the universe,
Right.
with more tools to measure that fact. I submit to you that it ought to be possible, even likely, that as our tools grow and we discover more things, fine. Then we get to a point where more powerful tools reveal the same phenomenon and not new phenomena.
How do you know
that?
that?
Tells,
Can
doesn't
I-
that tell you that you hit the limits?
But you can never know that.
Can I try something?
Well, yeah, Lee,
Yeah,
go.
because I wouldn't articulate it anything like the way that Marcelo does, but I have a disquiet with the dream of the search for the final theory, and let me try to express my disquiet and see if it overlaps and see if it addresses your question. Physics, the way that Newton taught us to do it, has a certain methodology, and the methodology is we isolate a little small part of the universe and we do experiments on the small part of the universe over and over and over and over again, varying the inputs, or what we call the initial conditions. And by doing this, we learn to separate out what are the generalities, what is true every time we run the experiment. If the experiment is throwing balls up in the air, we can throw them with different initial speeds, different initial directions, but something is always the same. And those things which are always the same we call laws, and we separate them from the initial conditions or the inputs to the experiments which differ. And
The laws are the things that are constant and repeatable
they're constant,
in time and space.
Yes, they're constant and repeatable. And this is the method that Newton taught us, and it's highly, highly successful. It explains the success of quantum mechanics of general relativity, which is always tested, if we're honest, with small parts of the universe and so forth. What is different about the period we live in is that we come to the cosmological scale. And at the cosmological scale, two things happen simultaneously which I think befuddle us and I think have thrown us for a loop. One of them is we no longer can do experiments over and over again. There's one experiment, which is the universe as a whole. Okay.
The Big Bang is a singular event.
So we're no longer in this place where we can separate out, quote, the laws from, quote, the initial conditions. That's the first thing that happens. And the other thing that happens is the process that Neil has discussed has worked so well that we're left with the question of not just what are the laws, but why these laws rather than other laws. And why the initial conditions, why it turns out that the initial conditions which give rise to our universe are very special. And why these initial conditions rather than other initial conditions. And at the cosmological scale, the method that Newton taught us to discover what the laws are gives us no grounds or no tools to answer the questions, why these laws, why these initial conditions. And at this point, we face a crisis.
Lee,
Yeah?
Katie, can't you create initial conditions on a computer and run different universe models? Isn't that tantamount to the same thing?
Yes.
Okay, so here is Lee in his angst that we only have one universe with one set of initial conditions, and we're hopeless in a Newtonian sense of being able to experiment with it. But isn't that what you do every day?
No, but we can't understand why these particular
It's the
laws
laws.
and why
I
these
think what he's-
particular initial
I
conditions.
think he's heading towards the multiverse.
I'm not heading towards the multiverse.
You are heading
I'll
towards the
give a room.
multiverse.
I'll give room for other people
So
if
there-
other people
well, you
want to
know
use
what?
this.
What-
You
the
are pushing
multiverse.
us towards the
No, no,
multiverse.
Multiverse.
Okay,
Katie, what's the multiverse?
Zip it. Zip it.
Before we head to the multiverse, okay, I think we're at a junction here, and the junction is, okay, the method that Newton gave us no longer tells us how to go ahead. We have two choices. One of them is to ask, what is the right method to go ahead and continue to do science? We have to change the methodology by which we try to understand the universe. That's the first choice. The second choice is the multiverse. The second choice is to say, well, the method we have only works on systems which are small parts of a much bigger entity, so let's invent a much bigger entity that our universe is a small part of and start to reason in the same way that Newton taught us, statistically and so forth, as if there were many, many, many universes. And just to jump in, my take on the multiverse, even having contributed my own versions of it, is that it's the response to taking Newton's method into a domain where it's not applicable and to failing to have the wisdom to invent a new method which is applicable to discovering what the laws are on a cosmological
I
scale.
think just because we don't have an answer to a question yet, for example, why are electromagnetic forces as strong as they are today? Just because we can't answer it now doesn't mean that we're not going to get there. I don't want to have to resort to saying, well, our universe has to have this value or we wouldn't exist, and somewhere over there is a different universe that has different creatures because their electromagnetic interactions have a different strength. I don't think so.
So
I
Lee,
think
I'm going to
that we're
translate
gonna
what she
answer
just
this.
said. She's saying, just because you can't figure it out
Yeah.
Oh, no, I agree with her.
doesn't mean the properties of the universe have to be different.
No.
Did I translate
think
accurately
the
there?
conception- No, I think the conception of laws has to be... Let me quote, for example, the first person to think seriously about the issue that I raised, as far as I know, was the American philosopher Charles Sanders Peirce. And he said in 1893 that the progress of science would advance to the point where the problem became not what are the laws, but why these laws. And then he said something I think has a lot of wisdom. He says the only rational way of accounting for why these laws, rather than other laws, is if the laws themselves are the result of a process of evolution. And I think it's that process of evolution that we have to discover and understand, and then we can do what Katie wants us to do.
Marcelo?
I was just want to make a remark before we go into this more philosophical discussion, which is basically we don't even know all the laws, and yes, we're definitely going to make progress. We are always making progress, and there will be answers to many, many questions. But I think it's a process that is not. We should not believe that we should get to an end. You know, I'm for the humility of the humanity. You know, like, yes, we're really smart, but to have the notion that we can find not just all the laws that exist in this universe, but also the laws that define the laws in all possible universes, and hence understand this one in particular, it's quite a which doesn't mean I'm a pessimist. I think we should go there. We should totally try. But we should keep in mind that everything should, in the end, be grounded in what we can measure of reality.
But can I just say, Marcelo, that we have had incredibly successful examples of unification. Obviously, certainly, our understanding of matter is more or less unified in an incredibly successful model where we understand that light isn't different from electromagnetism isn't different from weak forces or strong forces. Where do you draw the line? I mean, would you have drawn the line before that great success? Would you have said, we have we shouldn't be thinking about unification with matter, we'll never get there, and it's just too much to expect?
In other words, Marcelo, 100 years ago, what would you have been saying?
I would have been saying that the unification of electricity and magnetism is not perfect, only in empty space. And that is true. If you look at the sorry about this, guys. If you look at the Maxwell's equations that basically describe how electromagnetic waves propagate in space, they are beautifully perfect, symmetric, whenever you don't have any sources of electricity and magnetism. If you look at, sources, they're not perfect anymore. And just to make a comment about this, yes, we have unified, and I think the tendency of unification, of simplifying our knowledge of nature is absolutely key. That's what we all want to do. That's what we like to do.
But?
And in fact, the standard model, which is what Jana is talking about, is a magnificent achievement in which we can describe everything that we know of particles, in terms of 12 particles, and that's just beautiful. However, it's not a pure unification in the spirit that, say, superstring theory would like it to be, because each one of the forces, electromagnetism, strong, and the weak interactions, keep their imprint in the theory. And what we really want in the so-called grand unified theory or gut theory is that these three things become one. And the standard model certainly does not do that. It's really bringing them together in a sort of a patchwork way. And that is, in fact, one of the reasons why we want to go beyond that. That's one of the motivations for string theory.
Jim, have you gone beyond that?
How about
Where are you?
Brian is...
Well, it's been very interesting sitting on the stage and listening to my colleagues. But, and I am far from experimental physicists, as you can imagine. But this is why experimental...
Which means you're a theorist. Yes.
Something like that.
Yeah, okay. It's code for I'm a theorist.
I'm a theorist, exactly. But my point is that it is always the case that it is our experimental colleagues that prevent us from forming a religion, because it is always grounded in what they can measure, as Marcello keeps coming back to. And so although people can express either enthusiasm or dismay about where we are at a given point in time, I think that we need to be a little bit more humble and to understand that the process that we engage in is a constant flight from fantasy about what we would want to happen, and we query nature for that, and that query goes through experiment. So although this has probably been very entertaining for my audience here, I think that at the end of the day, we have to keep grounded in it's got to be about things that affect your lives, and those things are measurable things.
So where has this pursuit taken you?
Oh my God.
Where have you landed?
Why would you ask that?
I'm asking you that here and now. It's New York City. It's March 7th.
Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying... For a minute.
Yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code. You're saying it is computer code.
It's not even just is computer code. It's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we say are supersymmetric.
Okay.
Time to go home, I think. Where are we going to go? So are you saying we're all just, there's some entity that programmed the universe, and we're just expressions of their code?
Well, I didn't say that. Some of those
Like the Matrix? That's what you said.
Some of those codes are showing on the screen behind you right now. They don't look like codes, but these pictures, which we call adinkras, are graphical representations of sets of equations that are based on codes. So this is, in fact, to answer your question more directly, I have, in my life, come to a very strange place because I never expected that the movie The Matrix might be an accurate representation of the place in which I live.
Jim, may I give you an argument that we don't live in the Matrix?
Please. Yeah.
Very simple argument.
Give me one now, quick.
very simple argument. There's a property that the real world right down here has that no mathematical equation has, that no solution of an equation has, that no abstract object has. Here in the real world, it is always some moment, which is one of a series of passing moments. And a mathematical equation doesn't have a flow of time in it. It just is.
No,
and this means...
But Lee...
Wait, let him finish. Wait, I need him here and now.
This means that, to me, that the ancient metaphysical fantasy that we quote are just mathematics cannot be true, because in a world that was just mathematics, there would be no moment of time.
Why isn't there math as a function of time?
I'm sorry.
We solve those. These are differential equations.
But then you lay the solution out. X is a... Yeah.
You're mistaking... You keep using the word is, and I'm talking about the word describe. You see, the whole...
Described is fine, but
but
then we're
let
not
me
in the
let me
matrix.
finish, please, since we started with my discussion. The point is that it's fun to talk about some deep metaphysical essence that sits behind physics, but for some of us, it's about trying to find the most accurate way to describe where we live. And so my statement is that in the description of our universe, that is a supersymmetrical universe, which we were going to test in the LHC. If you believe that description, I can show you the presence of these codes. That's my statement.
That's beautiful, and that's fine, and I admire that. Seriously, that's fine. That's another beautiful piece of mathematics that may be explanatory or descriptive of physics, but that all I'm objecting to is that doesn't mean that we live in the mathematics. That means the mathematics is just descriptive of an aspect of the universe. And
well, that's a
we're
good
not
point.
in
Let
the
me follow
matrix.
that one up. Jim, just because, who was it? Eugene Wigner, who commented on the unreasonable effectiveness of mathematics that we just invent in our head, yet the universe follows, can be described mathematically. Mathematics is the language of the universe. Brian, math is your tool. So should we be amazed or depressed by what Jim tells us here?
I can't really comment on what Jim says. I find myself in the unusual position of feeling rather conservative on a panel when usually I'm sort of at the outskirts of
And by the way, the pictures Jim showed all look like spirograph images
I saw them.
from your
and
kids'
I don't
thing.
know enough about them to comment, but there is an interesting question, the one that you raise, about whether math is descriptive of the universe, or we are the math, or what's the role of math? Do you discover it? Is invented? I mean, I had a conversation, and I think you may have been involved in it, if not mistaken. The question was, is math the right way of going about trying to find deep physical law? And I said, look, I can imagine one day we'll encounter aliens, and they'll say to us, okay, show us what you've got to describe the universe. We break out our mathematics, and they look at it and they say, oh, math, we used to do that. Ultimately, a dead end, and then they show us what they have found. Now, the problem with that is I don't actually even know what I would fill in regarding what they would show us, because to me, mathematics is really the language of pattern. It's self-consistent ways of embodying pattern, and that's ultimately what we do. We're pattern recognition machines. We try to codify the patterns we see in the world around us in math, and in that way, we try to describe the universe around us. Does that mean we are the mathematics? I don't know. It becomes really hard to really know exactly what that means, but we have found that math, so far, is a potent tool for making predictions that we can test and confirm, and that's why I follow this particular trajectory.
Brian, we're going to have to very shortly go to questions from the audience, but I want to come back at you with a couple of questions that are sort of purposefully blunt. Okay?
Yeah. Sure.
So you guys have been at this string theory for running on 2 decades now, and Einstein, working alone, went from special relativity to general relativity in 10 years, working alone, and it was a brilliant piece of work, and there was an experimental verification 4 years after he came up with the idea. Here you have legions of string theorists working 2 decades, and you're sort of not there yet. Is there just not enough of you? Are you chasing a ghost? Or are the collection of you just too stupid to figure this out?
I mean, I think it's pretty clear it's the latter. No, look, Einstein was a singular genius, and making comparisons with him, I think, is perhaps not that representative. But putting that to the side, look, the questions that Einstein was trying to resolve, however deep they were still within a realm that was experimentally accessible within a couple of years, a couple of decades at most. We are ambitious, and we are trying to make a big leap to try to understand the universe on fantastically small scales and fantastically high energies. Why are we so ambitious? Because we have been so successful theoretically to date that the open questions in this line of research are the ones that we're now focused upon. They're much harder to test, and therefore we don't have the guidance of experiment to nudge us this way or that as much as in the past. Now, if we could solve these questions, I think we'd be answering some of the deep mysteries of the ages. Do you say, well, you haven't cracked it in 20 years, so it's time to give up? No, I think you say, if progress stalls, then you go and look at other directions. But as long as progress is carrying forward, and it is, you keep going and try to figure things out. You can't place a time limit on it.
I think your pace of progress is sufficiently slow that it has led to these other ideas exhibited on this panel.
Well, I don't
Because
know
you're
what
slow,
you-
that
you
Jim
know,
is finding
you know,
that we live in a matrix, and
Sorry
that,
to-
and that
you know,
Marcelo
again,
is
I think worry
questioning
about
the whole
some of-
idea of a unified theory.
Yeah, so I do worry about some of the things said on the stage, maybe giving the wrong impression. But the bottom line is this. You have no capacity, as far as I know, to judge progress in the field unless you're actually deeply reading the theoretical papers in the journals. Are you doing that?
No. Well, I presume members of, I presume that we got people here who. That's why I brought the panel here. That's why I brought this panel here. And apparently they're thinking up other stuff now because string theory is not satisfying them on some level.
Look, let me just say this. We have made great progress, and that I really think is not disputable. Have we solved all the key questions? Have we tested the theory? Those are the most vital things? No, but we've united gravity and quantum mechanics, at least on paper. On paper, we've unified all the four forces. We've incorporated key breakthroughs from the past that are now well understood within the context of string theory. We've been able to cure space-time singularities of particular sorts within string theory. We've understood black hole entropy within string theory. The mathematical contributions of string theory are absolutely unassailable. Time and time again, we've had great contributions. So to say there's no progress, come on, man, that's just not right.
Okay.
However,
While people gather to the microphones at the front of the stage, let me just get a quick reaction to Brian. No, Jana, we haven't heard from you in a bit. Quick reaction to Brian.
Well, I
invite
agree
you to come to the microphones.
I agree with Brian, mostly because his office is 3 doors down from mine. No, I do. I agree with Brian in the sense that progress is being made, but we all have to pursue other directions, occasionally think in a different direction than I can't say string theory is the mainstream, but then the flow of ideas, there's always going to be new ideas that come on the table. I don't think you can judge progress in terms of human scales. There's nowhere is it written that we have to solve problems in one human lifetime, that we won't have to work on problems for hundreds of years. This might be the first time that it's really been documented like this, but I don't see why we should be shocked that solving incredibly challenging problems may take more than one human lifespan.
And I confess, Brian, in spite of my diatribe there, I agree with Jana. There were some problems in the history of astronomy that took millennia to solve. So I'm getting on your case.
Neil, come on, man, give me a hug.
See, I could just unplug you, you see? I got real power here. Katie, where are you on this?
Supersymmetry. We haven't talked a lot about supersymmetry, which is an important ingredient in string theory, and there are aspects to it that come over to cosmology and are extremely testable.
So these are extra particles added to the model that we have for particle physics that explain some stuff that right now we can't explain.
For every particle we know about, there's a new partner. So for example, for the electron, there would be the selectron.
Selectron.
Selectron with the S, the supersymmetry in the front.
Cool.
Or the photon becomes a photino.
Okay.
And all of these particles decay to lighter ones, decay, 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 until at the end you get to the very lightest supersymmetrical particles, and those could be the dark matter. In fact, they're the strongest candidates for dark matter, and one of the major motivations for building the LHC. So the LHC can find
Dark matter particles.
Yes, and
Cool.
supersymmetry. And then dark matter detectors are currently, they're underground underneath the Apennines in Italy. They're all over the world. They're in deep underground mines in the United States. And they're looking for supersymmetric particles to scatter off of the detector, and then you look for that little bit of heat deposit. And every single one of these experiments that has happened in the last few years has seen anomalous, unexplained results. So,
That could all come together
yes,
soon.
so maybe Elena Aprile at Columbia University, she's the leader of the xenon experiment, and they're going to release data very soon, and that's the best bet that we're going to solve this
And then you're in
problem.
business. Then it's no longer an exotic particle. You're done.
Well, and if there's indication that if supersymmetry is right, well, that is one of the key ingredients in the building of string theories.
Marcelo.
However, if you look at the data coming out of the LHC in the last 2 months, it's restricting the parameter space of supersymmetry.
Not much. No,
A whole
it's
lot.
not. No,
I would say that-
it's misleading.
mean the
Their
Fermi
abstract is
results?
misleading.
You're both interpreting the same research paper
Yes.
differently.
Yeah, obviously.
Jim?
Well, all I want to say is that you need to understand that a large part of the discussion here tonight, and in fact, reminds me of the story about the blind man and the elephant. You know, they each feel a different part and think it's a different creature. I have a sense that that's likely what's going on in a lot of the discussion.
That the universe is an elephant.
Well, yes, and that
Written
we're
by the
blind.
Matrix.
And so the thing that I told you about information, ultimately, that would actually become part of string theory, not something different. If string theory is correct, this will be part of it.
I want to go to the audience right now. In order to make this efficient, because we're a little long, you direct your question just to one of the panelists, not to, look, can I get a comment from all 8 of you? No, one panelist, and we'll try to be efficient in your answers. Go.
All right, this one's
By
to
the way, I remember this, he was a little kid coming to Hayden program. I don't even recognize him. Aren't you in college yet?
MIT.
MIT, he's at MIT. Well, congratulations. He's been coming since he couldn't even walk.
This one's to
Wait,
Gates.
shouldn't you be in school now? Okay.
This one's to Gates, with apologies to Robert Frost. Some say the world would be written in Perl, some say in Lisp. But that aside,
You better apologize again to Robert Frost on that one.
You better watch out. He's at MIT right now.
I'll see you there.
I'll be looking for you in the infinite corridor.
Blame the admissions office. Anyway, do you have any predictions in your ideas, or any ways to test any of your ideas any more than, say, the guy over on the screen?
Well, first
You can take the blue pill or the red pill, and you'll find out.
I took the red pill. The work that I'm doing is, in fact, so theoretical that we don't understand yet whether it is even possible to complete the program. We have found these strange graphs. We know that they are equivalent to equations, and we have found in these equations computer codes, and so that's where we are right now. So I cannot give you a prediction. This work is less than 2 years old.
But it's not that you recognize that you will need a prediction in order to.
Someone recently asked me, said, well, you don't care about experiments, do you? And I said, no, that's exactly wrong, because you see, I have spent my career as a researcher worrying about supersymmetry. I would want to see an experiment before I shuffle off this mortal coil, so that I know that I did not waste my entire professional life.
We're good with that, okay? Right here.
I guess my question's for Lee. It seemed like towards the end you were talking about coming to a point where either you change the science or you go to multiverse theory, and it almost seemed like you were called out by Kate as though oh no, not multiverse theory, like it's a cop out. And is it or is it not? And that's really what I want to know. I want to hear a little bit more about that from you on that.
So is a multiverse a cop out?
My view is that it doesn't, and there are so many things that we've been mentioned here that we could have a long discussion of at very different levels. So, but my view is that it's very unlikely that the kind of multiverses which have a large or infinite number of universes existing simultaneously with no common chains of descent, it's very unlikely that those will lead to testable predictions that are successful. And I know that there's disagreement.
That doesn't mean that it's not true.
No.
Okay.
Science is not about what's true or what might be true. Science is about what people with originally diverse viewpoints can be forced to believe by the weight of public evidence. So, sorry.
I got to give him an applause. That was good. That was good.
Okay. So my view is that if, and this is, I should confess, in work with Roberto Mangueira Unger, which is in progress, and it's also inspiring a lot of my current scientific work. I'm interested in the idea that the universe is just that which we see already most of, and taking seriously Charles Sanders Peirce's maxim, which I did in my first book, Life of the Cosmos, was proposing a cosmological scenario in which the explanation for why these laws did arise through a process akin to natural selection. And thinking about that more seriously and more deeply in the last few years, it leads me to think a lot about the nature of time and the question of whether time is emergent, as many people in the quantum gravity world have proposed, or whether just space is emergent and time, in some senses, is really, really real, is not emergent, and whether if laws evolve and time is really, really real, whether there are new opportunities to do plain old-fashioned science, the way that Katie was saying. There's science where we make predictions and we widen our understanding and we widen our knowledge, because we're able to make predictions which are verified successfully. So that's in a nutshell.
That wasn't a nutshell. That was a coconut shell or something.
Anyway, thank you.
Okay. Next question here.
Okay, first I feel like maybe a little emotional closure on the debates. If you could kiss the back of his video head. Anyway, the question is just for fun, and if anyone wants to answer it, maybe no one does. Sort of in the spirit of Isaac Asimov. So forgetting LHC, forgetting even xenon experiment, if there's something that you could go to and measure, forgetting the continuity of space-time, what might you measure to get the deepest insight that you might want to see about the universe? Does that make sense?
Sure.
Let me go to Marcelo. Marcelo, you take that.
Jeez. I'd like to see gravitons. If I could see a graviton, then I would be for sure convinced that gravity has to be described quantum mechanically. Because you see, right now, we are so confused about what gravity is all over again that there are some proposals out there that gravity may not be a force like the other forces, which goes very much against the spirit of superstrings. And so if we saw a graviton and we're a quantum particle like a photon, that would be great. And if we're a chiral graviton, then that man would be a very happy man.
So it's not good enough just to see a gravitational wave. You want to get the actual particle in there,
Yes.
is what you're saying. Next question here, sure.
I guess I could aim my question to Dr. Green. When does the abstract become too abstract, where you can't even possibly, let's say, explain to the layman? I'm a biochemistry student. I took 2 semesters of physics and read some stuff on the side. I thought I'd be prepared for a talk like this tonight. I am abhorrently unprepared.
Okay, so Brian, why don't you take that?
Well, I think it's vital to explain these ideas in a way that someone without technical training can understand, simply because it's so enormously exciting what's happening at the frontier, and it's a shame when it's couched in language that many people aren't trained to understand. But in terms of scientific research and the progress that we make in one field or another, I don't think you judge it by how abstract it is. You judge it by how well it contributes to trying to solve unsolved problems, how well it contributes to trying to make predictions that you might be able to one day confirm. And, look, it could be that the final laws are right out there staring us in the face, frankly, and we don't have the mental capacity to understand it. So it may not be that we're coming up with ideas that are too abstract. the universe may have fundamental truths that we can't grasp. I mean, look, dogs are pretty smart, but I don't know any dogs that know the general theory of relativity.
Okay? That's it.
So
Plus, of course,
I-
Brian has the most successful books written on this subject ever. They were bestsellers, so somebody's buying them who are not scientists. And so there's some major fraction of the reading public that does receive the language, the translated language that Brian provides us. Next question, yes.
Yes, I'm one of those people who's not a scientist who reads these books. I'm a philosopher. And my question is directed to Lee, since he's grappled with philosophical issues more than anyone else I'm aware of. I was particularly enchanted by the trouble with physics and the earlier book, The Life of the Cosmos. Lee, how much of the problems that physicists are now dealing with in attempting to unify all the different theories of the physical forces, how much of that is as a result of a lack of conceptual understanding of, shall we say, philosophical insight? How much of it is due to being tied to an empiricist outlook?
That's an
I mean
interesting
by that,
question.
for instance, the old Newtonian paradigm that there are things out there
Yeah,
in the
so-
world, and relations are something separate from things.
Well, just so I understand, is it fair to reword your question in the following way, just because so I can believe I understand it? You're saying sometimes it's good to be driven by a philosophical expectation of what you would expect the universe to be, and that guides your experiment. And another way is just doing an experiment without a philosophy.
Well, something like that. But what I'm saying is that maybe our conceptual apparatus is sometimes that we inherit from our day-to-day experience is simply not adequate for grasping modern physics.
So I'm going to say two things that appear to contradict themselves.
And try to make this really in a nutshell. if you can.
One, science progresses because there's a diversity of scientists who have a diversity of viewpoints, predilections. Some of us are very pragmatic and empirical. Some of us are conversant with the philosophical literature and the historical literature. And I think it's important for the diversity, for science, that there be diverse approaches as well as diverse styles. Okay. I also think it's the case that we're coming out of a period which was dominated by a very pragmatic tradition, okay, which followed a period that was very philosophical. That is, the physicists who dominated the early part of the 20th century were largely people conversant with the philosophical tradition. And they achieved great things like the discovery of quantum mechanics and general relativity, and then they started to fail to achieve things, and the pragmatic generation that came after them achieved great things that they failed to achieve, okay, epitomized by people like Richard Feynman and Freeman Dyson. And now maybe we're in a period where we face again questions where we need people who are conversant with the philosophical tradition. But the most important thing is that the only thing that matters is real results that make contact with experiments. It doesn't matter how we get there. And therefore, the diversity of approaches is the most important thing for progress.
It's a good theme in many walks of life, actually. Next question here.
So I'll address this to Dr. Green on the television, because you talked about our ability to grasp. I wonder to what extent do the limits, our cognizance of the limits of logic, and this is a physics question, not a religious question, do we take that into account in our attempt to understand phenomenon? Do we ever think that they might be beyond the limits of logic, since we are, after all, embedded in the universe? And also, whatever happened to the anthropic principle?
Yeah.
Well, for the first question, we theorists all work within the framework of mathematics, which itself is based upon the logical structure within which the fundamental operations are constructed. So we really don't sit at our desks and counter a problem and say, maybe this is beyond logic. We say, maybe this is beyond the mathematical formalism that we so far built. Maybe this is beyond the theoretical ideas we've so far developed, and we try to push them, but all within the context of traditional logic, within the context of traditional mathematics. There are some people who push the boundaries and really do fiddle with some of the logical axioms to see where that may lead, but that's really not a mainstream activity among theoretical physicists. As far as the anthropic principle goes, well, that's this idea that we really touched on with these multiverse notions that came up a little bit in the conversation. I'm surprised, frankly, it didn't come up more in the conversation, because this is really where string theory has gone, and it's too late in the evening to go into it in great detail. But one thing that you really do have to bear in mind, when we observe the universe, our observations are biased. They're biased by the fact that we are here doing those observations. And we have to take into account that observational bias. There are things that we simply could not see, because to see them, we'd have to exist in a place that would be so inhospitable to our makeup that we couldn't actually be there. And that really is what the anthropic idea is about, taking that into consideration, and that is something that needs to be done across the board in science.
So a takeaway from you, Brian, there is that before you start abandoning the very foundations of logic, there's still much more to bring us from the field of mathematics in our search for truth in the universe.
Can I do?
Yeah, there's no evidence that we need to abandon logic.
Yeah,
I was just going to say quickly that there are examples in science, particularly last century, where we did confront decided limits in physics and in mathematics. So Gödel and Turing, for instance, were the mathematicians that realized that there were facts among numbers that we will never know, that it was an actual fundamental limit in the context of arithmetic. There were true facts among numbers that we would never know, and not only that, but most numbers were numbers about which we would never know anything. And there was also the limit of the speed of light, and maybe the limit of uncertainty in Heisenberg's understanding of quantum mechanics. And out of each of these things came incredibly creative scientific bursts. They were not the end of understanding, but they just squeezed all of that energy into a different direction. So from the limit of the speed of light, we discover special relativity. From Heisenberg's limit, we discover quantum mechanics. From Gödel and Turing, we delve into computer technology and artificial intelligence. So confronting limitations isn't necessarily an end. It's often a creative kind of beginning.
That's a brilliant point. Thanks for adding that. Yes. We'll go about another 7 minutes here. Are we okay in the audience? A reminder that at the end of this, the panel will be out in the Hall of Northwest Coast Indians, and you can bring your program, have them sign it, or I think there are books there for sale as well. So we'll take this another 7 minutes. So try to be efficient. We'll get through as many of you as possible. Go ahead.
How far do we take?
Well, who's this to?
I guess Mr. Green, but anybody who.
Okay, go on. Mm-hmm.
How far do we take the analogy with musical strings? They talk about.
We got to take that to Brian. Brian, you were on TV talking about string theory with a string quartet in the background. That seems like a stretch to me. How about do you?
But in particular, I was wondering what causes the vibration in these little particles, and is it the Big Bang and one proton extra and asymmetry created, and also you were talking about 10 dimensions coming. Is that coming from the 10 directions that the string vibrates, and how did they find those?
Yeah, so very briefly, I know that time is short. We didn't really say what string theory is, strangely, in this whole conversation. The idea is at the heart of matter are little tiny vibrating string-like filaments, and that's why we call it string theory. And as to the analogy with musical instruments, violins and cellos, this is one of the places in physics where the analogy brushes up very, very closely with the real physics. Were I to show you the equations governing the motions of the little strings in string theory and the equations governing the motion of a violin string, there are some very direct resonances between those mathematical equations. So this is a metaphor that really is, unlike many, right on target. In terms of what causes the strings to vibrate, that is, where does their energy come from, I don't know. That basically is the question. Where is the energy in the universe coming from? Why is there something, in essence, rather than nothing? We don't know the answer. We look out in the universe, we see that there is energy. If string theory is correct, a big if, but if it's correct, then the strings would be the most fundamental, microscopic carriers of that energy, and they would carry it in their vibrational patterns.
Okay. Brian, had I known you didn't know why strings vibrate, I mean, I don't know if I'm disappointed that you don't know this.
Just be careful with your way you summarize what I said.
Okay. I'll try. Next, right here.
This is towards Dr. Gates. Curious about your theory. You say there's computer code in these equations. Now, computer code is generally just instructions for a processor, and I'm curious as to what the instructions you're finding are, and if you're not sure what's to say that it's actually computer code. I mean, theoretically, the number pi has all the data that's ever existed.
Well, we say that they're computer codes.
You mean the digits in pi?
Yes.
Yes.
Okay. We say they're computer codes, first of all, because the structure of the equation is such that they dictate that there are certain things that are actually strings of ones and zeros. That's just digital data. But it's not just random ones and zeros. As I mentioned earlier, let me talk about something that you probably do every day, but I don't know if you're a computer scientist or not. Most of us sit at our...
Sounds that kind of fluency, I said.
Okay, well, most of us sit at our computer screens and we type on the keyboards, and we then send these, if we're using a browser, we're sending strings of ones and zeros elsewhere. But on the other hand, in the transmission process, there's always some fluctuations. So 0 that you type here because of static in line might be read as a 1 at the other end and vice versa. And so in fact, when you sit and type on the keyboard, your computer's doing something behind your back. Namely, it throws in a bunch of extra ones and zeros, and these things are called error correcting codes, so that the computer at the other end can look at the whole collection of what you typed plus what was sent and figure out if there were bits that were being flipped back and forth. And that's how you get accurate transmission of digital data. Among the codes that are used for this purpose are a special class of codes that are called block linear self-dual error correcting codes. They were first, in fact, the Shannon extended checksum code is an example of one of these things. These are the codes that we find buried in the equations. Not just any code, but these self-dual error correcting block codes. It's quite remarkable for anyone that I've talked to. We have no idea what these things are doing there.
Any literature out?
I'm sorry?
Do you have any literature out that...
I can give you technical references that almost nobody in the world can understand.
But Jim, I thought you had a popular level article on this?
Thank you. Yes, actually, so this past June, the British journal Physics World asked me to write a popular level description of what we have found. So in the June edition of Physics World, and it's published in London, the cover story is called Symbols of Power. It's about these weird symbols that have been showing behind us. We call these things adinkras. And so for a popular level description, yes, we've written that. But other than this one popular level description, it's all technical gobbledygook. And that's a technical term, by the way.
Gobbledygook.
Thank you.
Okay, I'm sorry, we're only going to have time for 2 more questions. I've just been cute, but you'll be one of them, so come on up to the microphone, sure.
Okay, yeah, hopefully this isn't like overly stupid question or uninformed, but I'm just curious whether...
I bet it's not.
Oh,
I'm going to
okay.
bet you, yeah.
Thank you, but I'm wondering whether like the quantum fluctuations, like random particles like popping into existence and out of existence, whether that would be, whether that could possibly be explained by particles moving through other dimensions into, say, a plane that we exist in, and if that's impossible, can you explain why?
Not only was that a good question, you're making everyone else in this room feel stupid. I just want you to know, okay? Just so you know. All right, so who wants to volunteer for that one? Katie, you want to hit that? Virtual particles coming in and out. Is that another dimension talking to us?
Well, we definitely know that particles pop in and out of existence. It happens everywhere all the time. And this gets back to this is what people think might be responsible for the dark energy. Only the problem is when you do the calculation, it comes out wrong by 10 to the 120th power, the 120 in the exponent. So in fact, there's much too much of this fluctuation going on in our calculations. So if you're going to include the amount in the other dimensions, it's not going to help. So I don't think that's a very good answer to your question, but this is at the heart of one of the deepest problems in all of physics.
Marcelo,
so not a stupid question.
I just wanted to add that, yes, theories with extra dimensions, when there are certain properties of these extra dimensions that they oscillate in certain ways, they can produce particles in 4 dimensions that we can actually detect, called pyrgons, I think. Sort of an old idea.
Gurdons?
P-Y-R-G-O-N-S, right?
Pyrgons?
Pyrgons.
Gons. That sounds like creatures out of Star Trek or something.
So yes, the presence of extra dimensions creates certain particles in 4 dimensions, or could create. I don't know if they're electrons, but they could be there.
Okay, I think we have the last question here. Welcome.
This is again touching on mathematics, and the question is, to what extent are our systems of mathematics and measurements subjective or objective, invented or discovered? Gödel, of course, talks about incomplete systems, but Einstein says, as far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. Any comments?
Yeah, Jana, why don't you take that?
Well,
this is what you've been working on,
well,
which gives you the final comments.
I'm still working on it. The interesting thing about Gödel is that he really was a strict Platonist. He actually believed that mathematical forms had concrete, objective existence. This world he wasn't so sure about. He wasn't really sure if his ordinary experience was created by his own mind, and he really had breaks with reality, but he did believe in transmigration of the soul and the idea that he would get closer and closer to a Platonic reality where it would all be perfect circles, pi, irrational numbers. And I think it's hard for most of us to follow that particular philosophy. I think that there is no simple answer to whether or not mathematics is the objective reality. I mean, Lee sort of brought up this idea that maybe it's just a description, but one which could never completely encapsulate. Did you say that, or am I projecting? Could never completely encapsulate physical reality. I mean, I think it's difficult to make a philosophical determination. I believe in being a bad philosopher, and at times being a complete objective realist in terms of mathematics when it's convenient, at times not being. But what seems to be true is that functionally, it's incredibly powerful. Functionally, it continues to work, and so we continue to pursue the ramifications of mathematizing the universe.
I want to live in a world with irrational numbers and rational people. Let's end with just, in 10 years, where's string theory going to be, or TOEs? 2021, where is it going to be? We're going to come right on down, and we'll end the evening. Go. But
I hope we have a quantum theory of gravity, whether it's string theory or not, and I hope that there is experimental test of it and verification of it. I think it could be one of several approaches, maybe loop quantum gravity, maybe causal dynamical triangulations, and maybe string theory, and we shall see. This is science, which means we don't know the answer.
Will we see it in 10 years?
Yes.
Good. How about you?
I think
2021.
I think it's a great time to be a scientist. We have great experiments on the horizon. We're going to see space ringing in gravitational waves. We have the Large Hadron Collider, and we have great mysteries. We know there are things we don't know. There's dark matter, dark energy. We know we haven't unified all the forces. So we have great mysteries. We have tools to approach those answers. I'm pretty optimistic that some of the pieces of the puzzle are going to fit together.
So the known unknowns are quite striking.
Yeah.
Are there any unknown unknowns out here? You wouldn't know, of course.
You're confusing me.
Marcelo, 10 years from now.
So yes, I think that at least in 10 years we'll have excellent data to possibly either confirm or rule out supersymmetry, and also know if the Higgs particle, which we also did not mention tonight, exists or not.
That's the famous God particle giving mass to all the other particles, right?
Well, it actually used to be called the goddamn particle, because they can't find it. So that's what Leon Lederman, who wrote this book, The God Particle, said. His real title was The Goddamn Particle, but the editor didn't like it.
The editor changed it, yeah.
So anyway, I'm optimistic in the sense that we'll have the data. I am very skeptical with notions that our ideas, when they go too far, always have something to do with nature. That this sort of extreme Platonism worries me a lot.
All right, Jim, 10 years, where are we?
Well, first of all, Marcelo just actually took my answers. I think in 10
Okay,
years...
should we skip you?
Yes.
That works. No, seriously.
Oh, you're not serious, I think that, in my pessimistic moments, I think in 10 years, string theory is not going to be complete. Because what's going to happen is a genius is going to have to appear, and that doesn't occur on anybody's time clock. We actually are going to need...
You're agreeing that the whole community is just not smart enough to figure it out.
No, because such people do appear.
No, but right now, all the people who have been working on it aren't smart enough. That's what you're saying.
No,
What are you saying?
because given time, one of them might actually be that genius.
Okay.
So in my darker moments, I think in 10 years, we are not going to have what Lee will probably be happy to hear, which is a background independent description of string theory. I think that's the absolute most important thing to find.
Okay. Katie, 10 years, 2021.
Dark matter, yes. Dark energy, we'll know a little bit more. Higgs, yeah, probably.
Again, the particle that gives mass to all other particles.
The goddamn particle.
The goddamn particle, yeah.
The gravitational waves, good bet. So a lot of the data are going to come roaring in, but is this going to prove or disprove string theory? Probably not.
Okay. Just give us a better understanding of the 4% plus the dark matter, not the dark energy.
And the supersymmetry, which is an important ingredient.
Okay.
And possibly the things Lee was talking about, these tensor modes, will tell you perhaps about something coming from the string epoch. So there's some hints there.
Brian, we're giving you the last word here because you had the first word. You're going to close this out. 10 years from now, 2021, where are you?
Well, look, here's my feeling. I really enjoy these Asimov debates, and to secure my place at the 20th anniversary Asimov debate, I'm going to hold back my answer until then.
Join me in thanking the marvelous panel. '11 Asimov panelists, thank you, one and all. Thank you all for coming. We'll see you again in a year, and we might see you just out in the Hall of Northwest Coast Indians. It's been a great evening. I learned quite a bit, and we will have the panelists there. I also want to just thank a few people. There's Suzanne Morris, who ran this whole thing, made it run as smoothly as these always do, and my assistant, thank you, Suzanne Morris. My assistant, Elizabeth Stachow. And we have a whole slew of volunteers. Collectively, I just want to thank them all for making these evenings run as smoothly as they do. We'll see you again next year, and we might see you again out on the tables. Welcome back to what is now our 10th anniversary of the Isaac Asimov Memorial Panel Debate. I'm the host and moderator, Neil deGrasse Tyson, at this institution. Oh, thank you.
Do we have books
Here at the American Museum of Natural History, I serve as the Frederick P. Rose Director of the Hayden Planetarium. Frederick P. Rose he's a great philanthropist. The entire Rose family, in fact, have transformed the landscape of the city in ways that have brought cultural enrichment to us all. The Rose Center is just one example of them. Part of that philanthropy that was going on at that time involved a way to remember Isaac Asimov. Isaac Asimov is no stranger to readers out there, author of more than 600 books. He is a New Yorker, did much of his research in the halls of the American Museum of Natural History, availing himself of our library system. And as a fitting memory to his legacy, his wife, Janet Asimov, and friends endowed this series, the Isaac Asimov Memorial Panel Debate. This is our 10th year, but of course that makes it our 11th panel. If you do the math, that's how it comes out. I want to thank Janet Asimov and the Asimov family and friends of Isaac Asimov for enabling this, what has become one of the most successful programs of this institution. I want to publicly recognize them for this. We have elected in this 10th anniversary of the series to reprise the subject of the original Asimov panel debate. That original debate was on theories of everything, specifically string theory, and what string theory is, what it means, How far has it come? How far will it take us? We thought that over these 10 years, maybe we should check in on string theory, see how they're doing. Oh, by the way, I meant to publicly recognize that we have 300 overflow attendees to this event in an adjacent room. I just want to say hi to them. Can I hear them? Yeah, there we go. Okay. We're not forgetting about them as well. So we're going to revisit this subject. We have two members of the current panel that were on the original panel. That'll sort of ground us with a 10-year